Hello, this is a short video on the material in Chapter 9 in our book on crashing. And I wanted to give the simplest possible example I could think of to give you the idea of what's involved in crashing, the purpose, and how it's done. Once you get the idea, I think it's possible for you to expand it to more difficult problems, although most of the problems we'll be doing will be very simple. In Chapter 8, we learned how to do scheduling, and hopefully you have that idea by now. Once you have scheduled the network and found the critical path, then you can use the network as a model. And in Chapter 9, we're going to discuss just two models. One is crashing model, which is a way to reduce the project duration. And the second purpose is to level the resources, or perhaps we would say in a simple case, just to level manpower, or woman power, if that was the case. How many people we're using, for example, per day on the job. And we level that in order to reduce ups and downs in resource demand. So we always begin with a network diagram. As you see here, I have an AOA diagram, and I've scheduled it, and you should be able to easily see how I did the schedule, beginning with the first node and labeling as 0, and then going up to node 3 to find a 3 as the early start, and then to node 7 and so forth. And the backward pass, finding the numbers in the triangles. Again, I'm assuming that you grasp this idea and you can do the network diagram as I've done here. What we're going to do now is we've noticed that the project duration here is 12 time units. We'll just say it's days. It's a 12-day project. Could be weeks, could be whatever. And we're saying that it's too long. We have to reduce the project to a shorter time. And so what I need to do is to reduce the project from 12 days to some shorter time. I'm going to just reduce it by 1 day for this simple example today in this little video. So I want to reduce the project from 12 days to 11 days. The question is, which activity should I reduce that will cause this project to reduce from 12 days to 11 days? There is no point in reducing any of the non-critical activities because they will not reduce the project time. For example, if I tried to reduce activity here, activity 7.9, and reduce it from 2 days to 1 day, the project would still take 12 days. So it would not reduce it. The only way to reduce a project is to work on the critical path, because the critical path is the path which controls the duration of the project. So I'm going to have to choose either activity 5.9, as you see here, or activity 1.15. And the way we do this, we choose, is based on what we call the cost slope, which is a ratio. It's just like if you're comparing cars in a race. Which car goes faster? The one that has the highest miles per hour. That's miles per hour. In this case, we're going to compute cost per day. So that's the rate at which the cost increases as we reduce the project. Inevitably, when you try to reduce time, you're going to increase cost, because in order to reduce time, you must add more resources. For example, doubling the number of workers, adding more equipment, whatever it takes in order to, or paying for expediting, whatever it might take in order to get the activity shortened, it will cost more. So I need to check on which of these two activities that are critical, I've marked them as the bold line here as critical activities, would be the best one to crash, as we call it, which is reduce, same as reducing. And what I have to do is to develop a crash normal cost matrix, as you see here. And you'll see a number of these in our textbook, which are simple to construct. However, to get the data sometimes is difficult because you have to work with experts who are knowledgeable in the project to let you know what is the best way and what does it cost to reduce a project. So you see here I've indicated for the two critical activities, I'm only going to do a ratio for these two activities because those are the only two I can actually reduce. So why do all of them? So I'm only doing cost slopes for 2 here. If the critical path was longer, I'd have to have more, of course, but I'm only doing them for the critical activities only. I just put an asterisk here because this is one of those activities that cannot be crashed. There always will be some in a project, or usually will be some in a project that cannot be crashed. So of those two activities, I see that the 0.66 is the smallest. That is computed by taking the time, the cost divided by the time. So just think of dollars over days, dollars over days. So if you look at the first, these numbers here, you'll see that the dollars are 8 minus $6 divided by 6 minus 3, which is 3. And that's 2 divided by 3, so the ratio is 0.66. So that's $0.66 per day is what it'll cost to reduce that project. Real simple math. There's nothing complicated about this. Don't worry about the numerical sign in the book. They end up with a minus sign, which is fine. It doesn't really matter, just as long as you're interested in the absolute value of the number itself. And in this case here, we have, again, cost 10 minus 8 is 2 divided by 2 minus 1 is 1. So the cost is $2 per day, or 2 time cost units per day. We take the lowest one, so the idea is to reduce the 0.66, which is the cheapest activity in this network. So what I'm going to do then is simply choose that activity, and I'll mark it on here. I'm going to choose activity 1.5, which is this activity right here, and I'm going to change that to 5 days instead of 6. And then I need to reschedule the diagram again. If I'm going to reduce this beyond, I'm not going to do it now, but typically we do these schedule reductions for many more than just 1 day. We'll do it maybe all the way to it can't be done any further. So we have all the alternatives identified. But for this case, this little example I'm giving you, I'm just doing it for 1 day. So I want to verify if the critical path has changed, and we can only, please make a note of this, you can only crash a project 1 day at a time. You cannot do it 2 days at a time. It may seem obvious, but don't risk it, because if it's at least, this is a simple diagram here, it's easy to eyeball it and see that you could go 2 days at a time. But normally in a more complicated network, you can't predict what will happen with the critical path. So we do it 1 day at a time. We find the single activity to reduce this one to 5, check again, it's going to now be 11 days, and we'll still have the float time shown there. I'll talk more about float time when I get to the next video, when I'll talk about leveling. So that's it. The new duration of our project is now 11 days, and I notice I did add up the cost here. The normal cost to do this is simply a sum of these numbers in this column. I'm sorry, it's in the wrong column there. The sum of the costs, 12 plus 6 plus 10 plus 8 plus 10, is 46 cost units, or dollars, let's say. The crash cost is adding up all the crash costs per day, total crash costs, and you see it adds up to 58. That would happen if we crashed everything. If we crashed every single thing on this network, we would reduce it, but it would be a foolish thing to do, because we're going to do it a critical activity at a time and not crash everything. Only crash those activities which actually reduce the project, and doing it 1 day at a time. So that's the idea of crashing. I hope that this video helps. It's very brief and crude, and I'm interested in your comments and questions you may have.